Achha, so again, just very quickly, this saying, how do you figure out whether a substance is pure? Pure substances, you check the melting and boiling points. They're supposed to have fixed melting and boiling points. Remember that for pure substances always. So result if pure, it will have a very fixed. I mean, you have to write the whole thing: melting point and boiling point. Okay, so that was uh, an easy question. Now he's saying substances that can be classified as elements, mixtures, compounds. We haven't really done elements and mixtures. We can skip that for now. Uh, Explain what is meant by the term fractional distillation. So, what was fractional distillation? I mean, you have to. It's a two-mark question, and you have to use words to actually describe that. I mean, fractional distillation is a technique where you separate
Is
substances.
it the
Yes.
is it the separation of mixtures?
I mean, it is a separation of mixtures, but which one? Let me get there. This one. Next one is fractional distillation. So you're going to write that it's a separation of mixtures where you have two liquids which are soluble in each other. So I specifically told you that it's when you have two miscible liquids. So what you're going to write over here is that it's a technique for separation of two miscible liquids. And you can give more detail, which is why do they separate? Because separation happens because of different boiling points. For example, ethanol and water. Ethanol has a lower boiling point, so it evaporates earlier, and you collect it at the other end by condensing the vaporized ethanol, and water comes in later. So you can add that as well. It's a two-mark question. Separation of two miscible liquids. Why? Due to the differences in boiling points. So that's going to be a precise answer. We can skip that. That's another one that's you're going to study later. Uh, so we did questions like this. I'm just trying to find. So this one. Uh, in this one, he's saying draw a label diagram to describe how you could show that there is more than one colored pigment in the green solution. So it's a 3-mark question, and you have to give a diagram of a chromatography experiment. He's saying draw a labeled diagram. We've already done chromatography, and which is why you should know how to draw a completely labeled diagram. The things that you're going to show in a chromatography diagram is you're going to show the solvent. There's going to be a starting line that should be drawn with a pencil. This is where you're going to place the spot. Uh, the other label is there's going to be a chromatogram. This paper is a chromatogram. There's going to be a solvent front, which would be at the top. So label all of them, and he's saying that the die contained, it was made up of 3 dyes. The question is saying, so you can add another dye like this. There's this dye over here, and it got separated into 3 different dyes. And why does separation happen? Because the dyes have different solubility. Because as the solvent gets absorbed by this chromatogram, it moves upwards. Some dyes are very soluble, some are not very soluble. If they are soluble, they would tend to travel a larger distance. Not soluble, they're going to stay behind. So this is the exact diagram: label chromatogram, label solvent front, label the starting line, show the solvent. The solvent level must always be below the starting line. You can place the dye on the starting line. You can show that. So it was just a label diagram that they were looking for, uh, and that's it. Now, the other one is, given a pure sample of chlorophyll, how could you show that the green solution from the grass contained chlorophyll? So you think some grass is crushed and mixed with a solvent propanone. The color pigments are extracted to give a deep green solution. Now he's saying, how could you show that you already have a pure sample of chlorophyll? How could you show that the grass uh, contained chlorophyll. What you could do is, and this is something that we did over here, which was that when we were talking about retention factor, I told you that if you have two dyes and they travel the same distance and they have the same RF value, which means it probably means they are the same dye. So you've got grass, you've got a green pigmented grass solution. I'm going to draw it over there. So he's saying, how could you show that the green solution from the grass contained chlorophyll? So what you can do is, like, let's say here's a chromatogram, and this is the solvent that you've dipped it in a solvent, and I think they did give the name of the solvent over here, which was propanone. So they said that it was dipped in propanone. Anyways, you're going to place the pigment. You're going to make a starting line. So that's your starting line with a pencil, and you're going to place the green solution from the grass. So this one is coming from the grass, and you're also at the same time over here. They've told us that you're given a pure sample of chlorophyll. So there's a very pure sample of chlorophyll. So there's another. So let's say this is the pure sample of chlorophyll, which you already have. So you've got a pure sample of chlorophyll which you already have, and this is the sample that you got from grass. I mean, you crush the grass and uh, the color pigments are extracted to give a deep green solution. I said, but anyways, chromatography is happening. So if these two contain the same, how could you show that the green solution contained chlorophyll? When the solvent gets absorbed, the dyes would start traveling with the solvent. So if they are the same substance, if they are the same chlorophyll, TK, remember chlorophyll is used for photosynthesis by plants. So the two samples would travel exactly the same. They're going to travel the same distance. Okay. And I'm teaching separation techniques, chromatography, and I mean, we're almost done. We're going to start a new chapter, which is going to be atomic structure. So coming back to this, so if you have missed this one, you can let this one go. Like in one day, probably we're going to start with atomic structure. That's going to be completely. We'll be starting from scratch. So, anyways, this one. Okay, coming back to this one. Uh, s- so he's saying, given a pure sample, how could you show that the green solution from the grass contained chlorophyll? So do two experiments. One with the green solution, and the other one should be with the chlorophyll. And you're going to write if they travel the same distance, or you can measure the RF value. So if they travel the same distance, or measure the RF value, and if it comes out to be the same value, that means if they travel the same distance, then they are more likely to be the same sample. Acha, then they are the same substance. Acha, next is we can ignore these questions, which we're going to study later on. Here's another chromatography experiment. So in this question, he's saying that enzymes are biological catalysts. They're used both in research laboratories and in industry. Enzymes called proteases can hydrolyze proteins to amino acids. The amino acids can be separated and identified. I said, remember one thing: a lot of questions are going to have all these stories, which really don't have anything to do with the question. They're just there. completely irrelevant. What he's basically doing is, at the end of the day, he's just doing, there's amino acids, and he's saying that they can be separated using chromatography. So remember, don't get confused with all of this. That's not part of your course. It has nothing to do with the question as well. So a lot of questions are going to be phrased in that manner. So the samples of the amino acids are placed over here, and there's the, I mean, this is the initial level of the solvent. So this is, you have dipped the solvent up to this point. Now he's also given you the formula of how to calculate the RF value. And some RF values for amino acids are already provided, and you are supposed to identify these amino acids. So we can just make you can either do this with a ruler. So it's the distance that is traveled by the dye from the starting line, which is this one. I mean, this is, let's say this is amino acid sample A. I mean, they've already told us that that's sample A. So it's the distance that is traveled by the amino acid divided by the distance, by the total distance which is traveled by the solvent. So I'm just going to make a rough guess. I think it's, if this is 4 centimeters, then that kind of looks like 10 centimeters. In the actual paper, you're going to use a ruler, and you're going to make sure on your paper you draw these lines, sketch these lines, to tell them clearly what you're doing, to tell the examiner clearly what you're doing, what you're up to. So I mean, over here, I'm just making a rough guess. That's going to be 4 divided by 10. The RF value would be the distance that is traveled by the dye divided by the distance that is traveled by the solvent. And it would be something, it looks something, I mean, it's obviously less than zero point 0.5. So uh, it's probably closer to zero point 0.4. So there is an amino acid that has an RF value of zero point 0.4. So A is going to be glutamic acid. And similarly, we can measure B. Uh, Now B kind of looks like, what distance is B traveling? I think it's traveling. If this is 7 centimeters, then this is probably the distance that is traveled by the solvent. That's already stated. I took that as 10 centimeters. So it's going to be 7 divided by 10. Distance that is traveled by the amino acid or dye divided by the distance that is traveled by the solvent. So that's going to come out to be 7 by 10, which is zero point 0.7. So that would be alanine. So that's just, I just solved this using, I mean, you're going to use, on your paper, you're going to use a ruler and actually sketch those lines. ठीक है. Adil, Amna, is this clear? Ajita, is this clear?
Yes, sir.
Achha, again, I told you, why do you need locating agents? Because, especially for biological substances, because you can't see them, they're colorless. I mean, you will have a spot over here, but you won't be able to see it. So you want to spray the chromatogram with something that would make the spots visible. Uh, for dyes or for inks, they are already visible, but for biological substances, most of them, they are colorless. So you're going to spray them with a locating agent so that they become visible. So that's why you spray them with a locating agent. Uh, so you're saying measuring RF values is one way of identifying amino acids on a chromatogram. Okay, so that's one way of figuring out what an amino acid is. Suggest another method of identifying the amino acid. So what you can do is, and on a chromatogram, right? So the other method is, you can you can take known samples. You can do chromatography with known samples. I mean, we did that with the chlorophyll thing. Like, for example, the chlorophyll question that we had. What you're going to do is, you're not going to measure the RF value. What you're going to do is, you're going to place a known sample over here, along with, you're going to place all the known samples that you already have. Let's say you have a bottle that's marked, and all the amino acids, all the 4 amino acids the ones that are given over here, you have a sample of them in a bottle. So you're going to place them on the chromatogram. So, and you're going to match them. If this sample B travels the same distance as one of the samples, that means they are basically the same sample. So, so the other method is forget RF values, do a comparison. Take a known sample. So, for example, this first one was glutamic acid, and you did chromatography, and it also traveled exactly the same distance as this one. So, if they are traveling the same distance, then that pretty much means that this known sample is actually this one. So that's another way. So chromatography, there are two ways of actually figuring out whether the substance of identifying a substance. One is you measure the RF value. The other one is you place the known sample that you already know of on the chromatogram and see, is that going to travel the same distance. If the two start traveling upwards, are they going to travel the same distance or not? ठीक है, and I'll send you the recording as well. ठीक है, I remember recordings उस पे just make sure कि they come up on the channel. ठीक है, every day. So next is again he's saying that which gas would diffuse faster. We've already done that. There's chlorine and there's bromine. So the lighter gas would diffuse faster. In the pure table, it's this is 35.5 plus 35.5. That's 71. This one is 80 plus 80, so that's 160. So this one is a lot lighter, so it travels faster. And so we're almost done with most of the questions related to separation techniques. Now, what we're going to do is we're going to just study not separation techniques. Let me just quickly find out where's experimental. So we did get this one. So we did experimental chemistry, which is basically just apparatus and how to use those apparatus. So this one is all about identifying this one. So the first one, most of these questions are kind of easy. The first one is a measuring cylinder, okay? And remember what each one of them is used for. Measuring cylinder is used to measure liquids, but it's not very accurate. And I told you that so it's not very accurate, but it's quick because it has a wider opening. So if you want to pour things quickly out of this, it would happen very quickly. The burette and the pipette. So the second one is a burette. It has a tap at the bottom. And the third one is a pipette. We did all of them. We can just very quickly go through them just a second. The board will load. So the burette and the pipette were very accurate. These two were very accurate. But they were slow because they had a very small opening and things would come out of the pipette or the burette dropwise. So if you want to pour something quickly into something, for that a pipette or a burette is not suitable. If you want to do things quickly, then for that it's probably better to do it with a measuring cylinder. Uh, but just a quick recap of these devices. I told you a specific purpose of burette, which was titration, which was that the tap at the bottom, it kind of helps you in reactions because especially when you don't know what amount of I mean, if you're trying to react X and Y, and there's Y present at the bottom, and you want to add X from the top, and you're not sure what amount of X is supposed to be added. So the tab kind of helps you. I mean, you can add some, then stop, then you can add some more and stop. And you can keep adding and stopping until you're satisfied that enough of the X has been added. So this is titration. In titration, you don't know what exact quantity of the reactant of one of the reagent or one of the chemicals is to be added. Remember, chemicals are referred to as reagents, ठीक or reactants. So if you're not sure what amount of reagent is supposed to be added, uh, so you use this tap at the bottom. You turn it on, turn it off, and at the end of the day, if you want to know how much of X has been added, there's going to be a point where you started and there's going to be a point where you ended. The difference is going to tell you what amount of X has been added to the flask. So burette was specifically for titration, but it's a very accurate measurement device. And the problem with the pipette was that the pipette had only one mark. It was very accurate and it was very slow, but it had only one reading, which was usually 25. I mean, there's only one mark on it. And I told you that it's specifically used to just pour things into different beakers. For example, if I make a solution in the lab and there are four kids performing an experiment, and I want to transfer a certain amount, a very fixed amount of liquid, and give it to each one of the students, I'm going to use a pipette. Every time it's going to fill up, there's a suction device which is known as a pipette filler. Uh, so the liquid fills up till that mark, or whatever that mark is, and you then release the liquid in the containers and you transfer it. So it's kind of used for transferring a very specific amount of liquid. But these two are very accurate. So this one is a beard, this one is a pipette. So you can answer this one. The next one is a student measures the rate of two reactions. Uh, Now, rate is basically a speed of reaction. So whenever you have to measure speed, there's one thing that is always needed. And what is that? Does anyone know? Like, how do you measure the speed of something?
With a stopwatch.
Okay, so you would need a stopwatch. Remember, you have to time things. If things happen quickly, then that means the reaction or whatever is happening, that's happening very fast. If things are happening slowly, that means the reaction is happening slowly. So whenever you're measuring rate or speed, you would need a clock to do that. So you're saying which piece of apparatus would be essential in both experiments. So you would need a clock, otherwise you wouldn't be able to measure the speed. Because that's one thing. Remember that to measure the speed, you always need a clock. I said this one. You're supposed to add 50 cm cube of acid, but quickly. Which apparatus would you use?
Measuring cylinder.
I just told you use a measuring cylinder. That's what you're going to use. The burette is very slow. The pipette is very slow. And the conical flask is not a measurement device. The conical flask had a very specific role to play. I said, this is your conical flask. And I told you that it had a very specific, it's just a container. It's not a measurement device. It's used for reactions because it's good, less spillage, less acid spray, and it you can collect gases easily because you can stopper it easily. You can shake it vigorously by putting a thumb on top of it. So mostly used for reactions, conical flask. But it's just a container, not used for measurements at all. I mean, it has no markings. Uh, Next one is a liquid turns white anhydrous copper sulfate and has a boiling point of 103. Which could be what could be the identity of the liquid? Uh, you forget this. You haven't studied copper sulfate. Leave this. Uh, Now this one. Now you've got an experiment, and clearly you can see that there is gas being collected. I mean, one thing. I mean, he's saying which reaction is being studied, right? So you can see a solid over there, right? So it involves a solid, and it's definitely you're trying to collect gases. Okay, that's what a measuring syringe is used for. So which experiment has a gas? That's basically option number B. In this reaction, there's a gas being produced. In the others, there is no gas. H2, I hope everyone knows hydrogen is a gas. So the gas particles would enter the measuring syringe. And the solid is this metal over here. The magnesium is a metal, so that's your solid. This one, a student was provided with only a thermometer, stopwatch, and a beaker. What could the student measure? Answer this one quickly. You've been given three things.
Option D.
Okay, so the thermometer is going to measure the temperature. The stopwatch is going to measure the time. The beaker doesn't measure anything. Okay, the beaker is only there as a container. That's just like the conical flask. It's not a measurement device. Again, you've got three things, and this one is a balance. Which equipment is needed to find out whether dissolving salt in water is endothermic process? So what that basically means is you're adding a salt to water, and you're just trying to figure out whether heat energy is produced, or will the temperature increase, or whether the temperature would decrease. So for that, you would definitely need a thermometer. Okay, so just imagine you're just adding salt to water, and you're just trying to figure out whether the temperature would rise or drop. Do you need a stop clock for that?
No. No.
Okay, so you don't need a stop clock for that, and you don't need a balance for that. The only thing you're trying to figure out is whether the temperature would increase or decrease. I mean, you don't even have to measure the salt. I mean, just add whatever amount of salt. You're just trying to figure out whether it's going to release, whether the temperature would increase or would it decrease. That's it. So this one is a repeat of the previous one. Uh, Again, speed of reaction. That's a stopwatch. You need a stopwatch for that. Uh, so then you have a student mixes 25 cm cube samples of this acid with different volumes. So remember, there are different volumes. So how would you measure the different volumes? What would you need to measure different volumes of the acid?
Measuring cylinder.
Measuring cylinder.
Okay, so you definitely need that. And then you say each time the student measures the change in temperature. So I mean that's obviously thermometer, and you would need a beaker. You would definitely need a beaker. I mean that's where you're going to store the, like, if you measure it, where would you put the acid? So that's your container. So you would need a beaker. There would be, which piece of apparatus is not needed. You don't need a clock because you're not measuring the speed. You're just trying to measure the change in temperature. I said this one. Now he's saying he's supposed to measure 30 cm cube of a liquid, but accurately. So which one?
Burette.
So that one
B.
is. That's definitely B. It's going to be a burette. It would be slow, but it would be very, very accurate. I said now this one is the reaction between solution P and solution Q is exothermic. That means that simply right now means temperature increases when solution P and solution Q are mixed together. A student is told to test this statement by mixing equal volumes of the two solutions and measure the temperature change. Which two pieces of apparatus would the student use? I mean, if you're trying to figure out the temperature, right? So it's either going to be a thermometer or it's either going to be B and D, and you're trying to mix equal volumes. So I told you a pipette always measures exactly the same volume. So hence the only option left is D, because I mean it has to be a thermometer because you're trying to measure temperature. Uh, so we haven't done this yet. As this one. Now, a student wishes to extract a colored solution from some berries to make an indicator solution. Which of the listed instructions should the student follow? Now, basically, you've got berries and you're trying to crush it to make a solution out of them. It's like making a milkshake. Like, I mean, you've got mangoes and you're trying to crush them and make a solution out of them, right? So, what is the correct order? I mean, what would you do? What's the first thing that you would do to the berries?
You would crush them.
Okay, so it's definitely either A or B. So I mean, you would crush them, and then what do you do?
Add a solvent.
Okay, you add a solvent. This is exactly what you do. Like if you make a fruit juice, you add water to it so that whatever comes out, it dissolves in it. And then you always filter. I mean, there's going to be a lot of stuff in that. There's going to be peels of the berries. It's like the skin of the berry would be there. So you would have to filter the mixture as well, right? So so it's going to be 1, 3, and 4. Just crush the berries, add some water to it, and then filter the mixture so that the seeds and the skin would get filtered off. So now this one is. So he's saying that this apparatus shown cannot be used to determine the melting point of sodium chloride. So what is this piece of apparatus? I mean, this is a method of heating a substance. What is it specifically called? Does anyone
A
remember what?
Bunsen burner?
It's it's basically. Let me just go over and revise what heating substances, right? So I told you about Bunsen burner. It's good for strong heating. Uh, but I told you that it's terrible if you're trying to heat it gently, right? So it's good for strong heating if you want to really burn something up. That's why you use a Bunsen burner. It has a very high temperature, uh, and I told you that you need a wire gauze, etc. thing so that the flame, because the flame is very pointy, you don't want to heat one point. You want the flames to spread. So you add glass beads, or you add a wire gauze, or there's a clear triangle. But what if you want to heat something gently? That's a water bath. Because if you heat, so this is heating the substance indirectly. Because if you heat the substance, the water would heat up, but the water temperature, first thing is that it never rises abruptly. Uh, like if you try to heat water or boil water at home, the temperature rises very very slowly. So it's a very gentle heating, and it never would cross 100 degrees centigrade. That's the maximum it would go. Even though the Bunsen burner is 1000 degrees centigrade, but the water temperature would not cross, and you can maintain that temperature as well, because water, when it's heated, it doesn't lose the temperature very quickly as well. So if the temperature reaches 50, you turn off the Bunsen burner. So for some time it would be maintained at 50, then it would start to slowly drop. You can turn on the Bunsen burner, heat it again. So you can kind of maintain the temperature as well. So it's a method for indirect heating, especially substances that are combustible. Like if you want to heat petrol to 50 degrees centigrade, you don't want the flames to be near it. So, so this one over here is a water bath. Uh, and in the water bath, there is this glass tube, which you can see, and that contains your normal table salt. So the temperature of this water, it simply cannot exceed, I say it cannot exceed 100 degrees centigrade. That's the boiling point of water. That's the maximum temperature liquid water would go to, and then it would turn into steam. Uh, so as long as you have liquid water, the temperature would not rise above 100 degrees centigrade. So he's saying the apparatus shown cannot be used to determine the melting point of NaCl. So why is that? Why can't you melt NaCl using this heating method? I mean, that's your normal table salt. What could be the reason? And what do you think the normal table salt that you have, what is the melting point of that? Anyone, any ideas? Or you can simply Google it. It's NaCl, it's somewhere. If you can just Google, one second. NaCl melting point, just one second. So that's around 801 degrees centigrade. Now, to reach 801 degrees centigrade, you can't really do that using a water bath. I mean, that's impossible. For that, you would need a Bunsen burner. Is that clear? ठीक है, Turan, is this clear? Saneem, is this clear? Salam. Okay. So for that, you would need a Bunsen burner. So gentle heating would not work. You won't be able to melt it. Uh, so that is probably not going to work. And so the melting point of sodium chloride is greater than 100. So that's why it doesn't work. So there's going to be a tick over there that the experiment is not working. And the other one is that sodium chloride dissolves in water. But that's not what's wrong with this specific experiment, because you can see that the sodium chloride is in a separate tube that's separated from the water. So that is not what's wrong with the apparatus, because the NaCl is in a separate tube. So that is, even though NaCl dissolves in water, but it's in a separate tube. So that is not an issue. So that's why the option is going to be B. I mean, the thing that's wrong with the experiment is this one. I mean, you've already taken care of this one. You've already added NaCl in a separate tube. So, which is why it's not going to mix with the water. Uh, so how would you know that a liquid is pure water? Because when you boil it, it's going to boil at a very fixed temperature, which is going to be 100 degrees centigrade. So that's that. This is collection of gases. This is for heavy gases. Heavy gases settle at the bottom. So I told you about gas collection, but heavier than what? Heavier than air. Air, I told you, had a mass of 29. So any gas that's heavier than 29, okay, air is mostly nitrogen and oxygen. So any gas that's heavier than 29, that would be, you're going to use this one. This one, gas or measuring syringe, could be used for any gas. And this is over water. You bubble the gas through water, and the gas travels upwards and forms a pocket over here. So this is also a good way of collecting gases, but this is for gases that they should not be soluble. You don't want the gases to be soluble, because if they are soluble, the gas would mix with the water. So you don't want that to happen. So an experiment is carried out to investigate the rate of reaction when calcium carbonate is reacted with hydrochloric acid, and the volume of carbon dioxide given off is measured at different time intervals. So diagram shows pieces of apparatus used to collect the gases. So which piece of apparatus is suitable? Uh, it's suitable to collect and measure the volume of carbon dioxide. So that's the question. Now this one is not a suitable method of measuring the volume of carbon dioxide gas, because I mean, it's a good method of collecting carbon dioxide. All the gas would settle at the bottom, so you can collect it. But the problem with this apparatus is you wouldn't be able to actually see the carbon dioxide gas because it's invisible. So if the container gets filled up till this point, I mean, you can't even see to what point it has been filled. So you can't really see the gas. You can collect the gas, but you can't really see it. So you can't really measure what amount of gas. So imagine a glass of water where you can't see the water. So if you can't see the water, how would you know how much water is present in the glass? So imagine this gas jar that's full of carbon dioxide gas, and you can't see the carbon dioxide gas, so you can't really tell whether it's half empty, whether it's completely full. So he specifically said that he's trying to measure the volume of gas that's given off. So the first one is wrong. Can't really use that. The second and the third one are specifically used for measuring the volume of gas, because as more gas enters, what's going to happen to the piston? It's going to get pushed back. So you can clearly see that this is the gas. This is the amount of gas that has been collected. And similarly for this one as well, as soon as more gas fills up, you can clearly see that there's more and more gas filling up. So you can measure the volume of gas. Okay. So is this clear?
Yes, sir.
So try going through the worksheet. Try doing the MCQs. We're going to start atomic structure tomorrow. Okay. That's basically when. Uh, I mean, this is your basic things. Most of the things were basic, but now we're going to start atomic structure and chemical bonding in the next class. Okay. So take care, everyone. See you tomorrow. Allah Hafiz.
Officer.